Hello, class. We're just going to try and quickly cover some audio notes, make this as a video for you so you can watch it and hear me kind of quickly go through some of the ins and outs of this Galaxies chapter. As of right now, the time that we are going to be out of Class 4 is still 3 weeks, and at the bare minimum, we should be able to cover this entire Galaxies chapter. I will post a study guide, which is kind of like the chapter summary, as well as these video notes. Luckily, this is a short chapter, so it shouldn't take me that long to get through all of this. Like I said, just keep checking Classroom for whatever the assignment might be, so that you can, get the work done and try to get through this as painlessly as possible. So with galaxies, we've talked about what galaxies are any number of times. Okay, we should know by now that they are large groups of stars bound together by their collective gravity. This is a picture of an actual galaxy out in the universe that is not too much unlike our own, the Milky Way galaxy. It's got a high concentration at the center, a high concentration of stars at the center, and these spiral arms. Galaxy is spinning, and if you are talking about our own galaxy, it takes us about, I think, 250 million years to do one lap around this. But this one structure here is made up of hundreds of billions of individual stars, hundreds of billions of individual solar systems, which is just a lot to consider. Okay, and there are more of these in the universe that we can even really count right now. There's probably more individual galaxies than there are stars in any one individual galaxy. So imagine hundreds of billions of these, each with hundreds of billions of stars. And each of those star systems might be as intricate and varied as our own solar system, with planets, moons, asteroids, comets, meteors, and everything else. So this chapter are just to talk about, we're getting deeper and deeper into space now. So we were initially very local, talking about planets, and then we were talking about stars in our galaxy, and now we're talking about other galaxies, across the span of the entire universe. So some of the basics: huge individual group of individual stars, star systems, star clusters, and gas all bound together by gravity. When you look at a picture of a galaxy like this, you see one big bright spot at the center, but it's not one big bright spot. It's just that's where the concentration of stars is really, really high. If you guys may remember that I showed you a picture some time ago of a picture of Andromeda Galaxy, and you keep zooming in on it, and you see that all the stars, there's just a lot there, and it seems like they're all really close together, but they're not. They're all individually bright, and so it makes for one kind of concentrated center. Sorry, I had to pause that for a second to find this picture, but this is a picture taken by the Hubble Space Telescope of the Andromeda Galaxy, which is the closest galaxy to us at about 2.4 million light years away. And you see here's very close to its center. It looks like one big central thing. And you get outer towards the outer regions, it gets kind of more and more dissipated, not that high concentration. But this is such a high resolution picture that if we keep zooming, and hopefully this shows up okay on this video, as I keep zooming, and as you get closer and closer and closer, each of those individual points of light are each individual stars. And again, try to think about how small of a section of this great big thing it is that we're just looking at. And if you look at the galactic center here and you try to zoom in on that, they're so close you're not going to be able to differentiate individual stars. But each of these individual spots that you're seeing there are all an individual star. And Andromeda is not too much unlike the Milky Way. We just obviously can't get this view of the Milky Way from inside the Milky Way. So again, I know I've shown you guys all this before, but just kind of an interesting way to look at it. When you look up in, say, a region like here where they're really spread apart, there's still just countless numbers of stars that you keep zooming in and zooming in and zooming in, and it gets crazy. So all of them are held together by gravity. And when you look at a galaxy like this, and again, this is only about half of the Andromeda Galaxy, you think is the center of the galaxy is kind of the urban center. Think like, downtown of some major city, we'll say Chicago. And then as you work your way out, you get closer and closer to the suburbs. And you get further and further out, you're more in the rural area where everybody's a lot more spread out. And using that model to kind of help us explain galaxies can be useful. Sorry, get back to our slideshow here. So, concentration of the stars is the greatest at the center. At the center of every galaxy is believed to be a supermassive black hole. We'll talk more about that in a little bit, but these aren't just your black hole that were formed from a star dying. These were black holes that, are the mass of millions, possibly billions of suns that are still consuming mass, still consuming matter from other surrounding stars. Galaxies can collide with each other, and they do gravitationally tug on each other. Our galaxy is going to collide with Andromeda in a number of years. And like 5 billion years or so, Milky Way and Andromeda will collide. And I'm going to skip ahead a slide or two since I'm mentioning that now. That if you look at this GIF replaying here, this is, I think, from an excerpt of Cosmos, but our two galaxies are going to collide and twist and eventually form an entirely new galaxy. A kind of time-lapse photo here of view from Earth of this happening is here's our Milky Way now. You see this disk here and see that little dot there, that's Andromeda. A little bit more time goes by, it's getting closer and closer. And the two start twisting and tangling with each other. And ultimately, this is how that's all going to look like from Earth. So the gravity of galaxies, their combined gravity is pretty impressive. We imagine at least 100 with a B galaxies in the universe or so. But this number could be trillions. It could be much, much, much higher than that. Look at this graphic here. Again, the center of that, and right at the center of that, that's where the supermassive black hole is. All these stars are orbiting around that. And that's true of the stars in our own galaxy as well. Here, our sun and our solar system is located like in the suburbs. Not way out in the rural area down here, not really close to the urban center, but kind of halfway out. And the diameter of our galaxy is about 100,000 light years. Meaning it would take 100,000 years, one with 5 zeros after it, for a beam of light to travel from one side to the other side. Since we're about halfway out from the center, that means that we are about 25,000 light years from the center of our galaxy. So talking a little bit more about our galaxy specifically, estimated 100 to 200 billion stars alone in our galaxy. And that's pretty typical for a galaxy of our size. It's 100,000 light years across, about 1,000 light years thick. Okay, it's disc-shaped, it's flat, but it's still, by flat, we mean 1,000 light years thick. So not that flat, but compared to its width, it is pretty flat. So it's 100 times, this number is 100 times this number, so it's 100 times wider than it is thick. The sun and the Earth and our solar system is about 25,000 light years from the center, and it takes about 230 million years or so, I think that's close to the number I said before, to orbit the galactic center, which if you do the math there, we are moving with an average velocity of around 500,000 miles per hour. Our entire solar system is moving together at that speed relative to the center of the galaxy. The Milky Way's age, the oldest stars are about as old as the universe, but the age of the actual Milky Way, the disk of the Milky Way, is only about 10 billion years. So, keeping in mind that the universe is about 13.8 billion years old or so, 4 billion years before what happened before our disk of the Milky Way even kind of came into existence. Just here's a cool view of the Milky Way, and we kind of show pictures of other galaxies, but to compare them to the Milky Way galaxy. But it's important to remember that we can see the Milky Way galaxy. It's just we're viewing it from inside of it. So we see that milky streak, passing through the sky, and this is one of any number of different pictures that you'll kind of see like that. But remember, within this, okay, so imagine, we're in this disk, we're looking at it from here, so we should be able to sense the middle, we should be able to sense the edge. So where exactly are those things? Keeping in mind, remembering at the middle is a supermassive black hole. It goes by the name of Sagittarius A. This is an artist's depiction of that black hole. This is obviously not a real picture, but we have this thing at the Milky Way center, and it is it's big. We're talking millions, billions of solar masses here concentrated at the center. It is consuming stars at the center, and that's kind of how it got so big. If we're looking about where to find this in the nighttime sky, you're obviously not going to be able to see this, but it's called Sagittarius A because it is within the constellation Sagittarius. So if this may not always be perfectly south, but the two constellations, you have the Sagittarius constellation over here, and here's the teapot. It's like part of Sagittarius, easily recognizable over here. We can see it over here, and you see this milky path and these dark patches right in the center of that. And again, it will go up. You're not going to be able to see that. It just is like the brighter part of the Milky Way path that we see through the sky. That's where we've figured that our galactic center is just kind of a nice semi-arbitrary point in the sky. And if you located that point, you wouldn't really see anything special other than if you went to a very area with at a higher altitude or way out in the wilderness somewhere, and you saw the Milky Way path here. That's obviously pretty cool to see, and it would certainly be within that path. So Sagittarius A, that is the name of the supermassive black hole at the center of our galaxy. Here's kind of an infrared view of the center of our galaxy, and we zoom in at it, and this is kind of the best we see here. As that black hole consumes stuff, we see that happen. This is before a flare-up, and then you have the flare, and you have a post-flare, but somewhere shrouded within this is that kind of monster, sometimes referred to as the monster of the Milky Way, is the giant black hole that we have at its center. And there's like thousands and thousands of black holes, probably millions of black holes scattered throughout our galaxy, but this one is obviously the most consequential, the most important of those. And again, this is an image in X-rays just because it's so energetic and it's so high temperature that high energy radiation like X-rays will be what this is emitting in. So just a little bit different view of kind of what we had said there. As far as types of galaxies, we have 4 primary types, and this is going to be a big focus of this section. They're pretty easy to tell apart. You have spiral. This is kind of like our galaxy is, one central core, and you have these long spiral arms, looking like, when the water going down the sink or your toilet flushing. Very similar to that, you have a barred spiral, where it's still a spiral, but in the middle you have this kind of weird barred section here, where it's not just a center point, but it's a center, and then 2 bar arms come out, and then you have your spirals radiating outward from that. A little bit better view of that guy. So spiral, barred spiral. Elliptical is also really easy to tell. Instead of a disk, it's like an egg shape. So galaxies like these may appear differently depending on how they're oriented to us. If this is like facing us edge on, we wouldn't really be able to see all this, but the wide side is kind of facing us right now, as is this one. But for elliptical galaxies, it is, regardless of how it's oriented to us, we're going to see it as pretty much the same shape because it's not a flat disk. So there's no way for us to see it edge on. It's just this big kind of cloudy halo of stars going around some central point. So you kind of see that egg shape there. And again, regardless if it's facing us this way or that way or this way, it would always kind of look this shape. We also have irregular galaxies that you see over here that are neither. They're, maybe the result of a collision of two galaxies, and they're still trying to organize themselves or whatever, but it's just obviously a weird shape. There's no really spiral arms. It's not this nice organized cloudy halo, and it's just, it's called irregular because that's exactly what it is. It's irregular, and it's kind of weird looking. You have some other types that there's not going to be as much of a focus on, but a couple I do want to mention. Peculiar galaxies are ones that have structure but don't really follow any kind of spiral or elliptical pattern. So they're peculiar. So peculiar is kind of like structure but nothing super organized. A lenticular galaxy is kind of a combination of both elliptical and spiral. So again, they don't really have great spiral arms, but they are still in a halo. So down here is kind of an example of one of those, is a peculiar. Irregular, we already mentioned. So irregular is neither. Lenticular, which is a kind of a new fun term, is both. And peculiar is exactly peculiar. They have some properties of each, but can't really get categorized in anything else. You have this other category, ultra diffuse galaxies, which are basically galaxies that are really spread out. These are going to be less important for our purposes, but all, good names to know. I do ask you a little bit about lenticular as well as irregular. So lenticular is both spiral and elliptical. Irregular is neither. Here's another cool view of the Milky Way galaxy as seen from Earth. You see a nice mountain here and some streaks across the sky, and you see that kind of milky path. When we're looking at it on a clear night out, we should be able to see that running from north to south. Ish. Here, this is what we call the tuning fork diagram of galaxy classifications. We don't need to have all this memorized or whatever, but basically you have elliptical galaxies, and then as ellipticals become less elliptical, they can either be spirals or barred spirals. Those lenticular galaxies that are both, they're right here. They're kind of the tipping point of when they go from elliptical to either spiral or barred spiral. If you ever see any of these terms, SA, SB, that's what they refer to. And we don't need to know all those, but just know that this is kind of how we organize them. The most elliptical would be E0, and then E7 is less elliptical, S0 is lenticular, irregular wouldn't be anywhere on here. Just another view of the same thing. So here's some different pictures of different galaxies. Here we have an irregular galaxy. Here, different types of elliptical. E0, that's very elliptical. It's very circular. E7, it's starting to flatten out a little bit. Here we have another elliptical, a little bit of a barred spiral. Here's more of a concentrated normal spiral. Here's a picture of what we call the Sombrero Galaxy, which is kind of a flat galaxy. Here you have the Sombrero Galaxy, and here's where we see it. It's kind of edge on, like I was talking about. Like ones like this are facing us. This is more edge on, so it's hard to tell. But this is a spiral galaxy. It is an unbarred spiral galaxy, and it does look like it has a little bit of an elliptical nature to it. But this is actually a spiral galaxy. So I should be able to give you pictures like this, these, and you'd be able to tell me, well, that's irregular, that's elliptical, spiral, or barred spiral. Kind of some of the more easy aspects of this chapter is just being able to tell the difference between those few categories. So this actual slideshow will be posted on Classroom, as well as this video of me kind of walking you through it. And we're coming around 20 minutes on this video here, so I'm going to try not have this be too incredibly long. But if you'd rather just kind of read through it without, kind of me doing voiceovers on the whole thing, that will be there for you too. Moving right along, you guys should have watched a few videos on this the other day. There's a chance you might do this before that, but either way, you either already have or will watch videos about the Hubble Deep Field, which is actually pretty interesting. So this was a picture taken by the Hubble Space Telescope in 1994 or 5, where basically, you know, how the Hubble Space Telescope is exactly that. It's a telescope that's in orbit around the Earth. It was originally deployed in the early 1990s, like around 1990 and 1991 or so. And, you know, it gives us the best pictures of deep space that we could ever got. And it can do that because it's in space, and it doesn't, images aren't going to get distorted by our atmosphere and other factors. So, like all telescopes, they kind of get rented out for different research by different scientists at different points. And scientists wanted to rent this one out to take a picture of, instead of looking at say a neutron star or a star system or whatever, say, no, I want to point it at a totally empty point in space and see what comes back. And we've since done this a number of different times, but this was the first one, and this picture really changed what our view of the universe looked like. Is they took these pictures over the course of a week and used different wavelengths of light and so forth to take these pictures. And this small little patch of sky that I took pictures of, once they got the images back, all of these galaxies came out. So again, a completely empty patch of sky, and each of these points of light in here are each individually galaxies. And this is, in the one video, they said it was as much of the sky as would be taken up as if you held the head of a pin an arm's length away. Another comparison I have here is if you held a tennis ball at 1,000 meters away. So think about a tennis ball being held about a football field lengths away from you, how much of your field of vision that would take up. That is how much of the sky we looked at by taking this image. And all of these galaxies are in here, thousands upon thousands of galaxies in here, which is definitely surprising, is that this kind of completely changed how many galaxies we think are in the entire universe. So you have galaxies of many different ages in this picture. The largest, probably the brightest ones, although there's probably a couple stars in here that just happen to be in the foreground, like this guy. But most of these are all galaxies. And it's just fascinating to think that just in that small section of sky, we have this many galaxies. Every little small point of light that you could barely recognize in here is its own unique galaxy. And this picture is a little bit deceptive, and this is an important question if I get to assess you guys in this stuff, is this is deceptive because it's not just a picture of space, this is a picture of time. A lot of the galaxies in this picture probably don't exist anymore. They're from so far away. They're from the beginnings of the universe. And it took that long, 10, 11, 12 billion years for the light from that galaxy to get to us. So this is a look back in time. So the furthest away objects in here are a window into the very beginning of the universe. So it is a little bit deceptive. It's like, oh yeah, the sky is just completely filled up with galaxies. Yes, but also no, is that while we are still seeing these galaxies, a lot of them aren't there anymore. The majority of them are so many millions and billions of light years away. They have, since the amount of time that they released that light and sent it in our direction, they have evolved and changed and may not even exist anymore. So this is what we call the Hubble Deep Field. This is deep space, the deepest pictures of space they would taken up to that point. So this is not just deep space, this is deep time. This is the furthest back in time that we've ever looked. And just like anything in the sky, this is an active window into the past. But this is as far into the past as we've ever really been able to see. And so in the one video that you guys watched in one assignment, that was a picture that changed astronomy. And since then, they took a Hubble Deep Field South a little bit later in that year. In 2004, they took the another picture called the Hubble Ultra Deep Field, which, let me just make this a little bit bigger for you here. This was a section of sky This is kind of in the southern hemisphere, but a small section of sky here. And they kind of did the same thing and just looked for a long period of time. And they got this. They got all of these galaxies. And this is the deepest look into space that we've ever had now. If you're going through the slideshow and want to play this video, it'll probably show up weird now. If I can get it to play. So I know you guys aren't going to hear the audio very well, but you should at least get a sense of what the video is doing. Oh, I just paused it. But as this video plays, it's a 3D image of this. All these, you move past you, and as you get further and further into this image, it'll show up better if you play it on your own computer than watching this recording. But it's pretty neat, and again, you get that sense that dimensional thing. It's a three-dimensional thing, and the faintest things are so far back. It is literally a window into the beginnings of the universe, which is, makes a whole bunch of all kinds of questions pop up in your head about how we're seeing the beginning of the universe. Yeah, kinda. About as far back as we can see. We're seeing these ones that are showing up now. These are some of the first galaxies that even exist. So I don't know if you want to take a look at that a little bit more closely. So there was 2004 was the ultra deep field, and we even had more intense than that. Is in 2012 we took another picture of this. You had the Hubble extreme deep field. So you have the Hubble deep field, the Hubble ultra deep field, and the Hubble extreme deep field. Annoying that all their names are so similar, but each speck of light here is a galaxy. Some of which are about as old as the universe. So again, we look at these pictures and makes us how many galaxies can possibly exist in the entire universe. Is that the observable universe is estimated to contain 200 billion to 2 trillion galaxies. And it looks like all of them are like in this picture, which is just crazy. And again, the picture is deceptive because they're not all still there, even though we can still see them. They are so old that they don't exist anymore. We're seeing things that are so old, like they don't exist. It's just the light has been traveling to us all this time, and in the meantime, it's continued to live, die, expand, collide with other galaxies, whatever might else go on. So again, 3 terms: deep field, ultra deep field, and the extreme deep field. So these are all images taken by Hubble. And there's going to be a kind of a replacement to Hubble that's going to be released in a few years called the James Webb Space Telescope, which is actually going to be able to see even further into space. I think it was, the last I checked, it was slated for launch in like 2021. And it's going to be getting even better pictures and be able to look even a little bit deeper, basically to the limit of what we can even actually see. And here is a good graphic of that. So the Hubble Deep Field, this is its outer limit of how far back it could see, about 1 billion years after the Big Bang. So about 12.7 billion years ago was its limit. The ultra deep field got a little bit further than that, only about, half a billion years after the Big Bang, which, again, we're looking at the very first galaxies that can exist. The first stars back there are this is further back in time. So again, we're not looking further and further into distance. We're looking further and further back into time, to the point where you get to when there wasn't even light to see. So you had this dark era, this dark age where the universe was too dense for even light to pass through. A similar type of picture, but the Hubble Space Telescope, this gives you a graphic. You can see back to the first galaxies. But this guy here, where it says the JWST, that is the James Webb Space Telescope, that is going to be the kind of the replacement for Hubble. It's going to be able to see all the way back to the first first galaxies, but basically right after the universe first had things that you could see. Because from the Big Bang to here, there was stuff, but the universe was too dense for light to even pass through. So it's pretty much impossible to really see past that era. So you had this dark age. And the past that is the cosmic microwave background, which we can see, but that's a little bit harder to explain, and will get brought up a little bit later on. So speaking again of just like how small of a patch of sky these deep fields were, so this XDF, so the extreme deep field, here's the moon, just to give you a frame reference. So the moon, if you hold your thumb out at arm's length, your moon takes up a little bit less space than the tip of your thumb does. And this is how much sky we looked at. And just out of a little patch of empty sky like that, there were so many galaxies. So again, translate to that the entire sky. And again, the picture of the moon here is only for frame of reference. So the moon is about half of a degree, and this is like 100th of that or 1/10 of that or something. And we can only assume that we look at any other patch of sky and there's going to be a similar number of galaxies. Think about all the little patches that we could take up of the sky of this, and we look in every direction. We see this if we look deep enough and hard enough. So a few other odds and ends here is you have, just our galaxy. Remember, it's a disk, so it's flat. It has kind of a central bulge. It's about 1,000 light years thick, 100,000 light years wide. Our solar system is about halfway out here. So I want you guys, I'll post this video separately because it's actually pretty interesting. And they talk about, well, how are galaxies grouped beyond just galaxies? There's a local group. There's a Virgo supercluster. There's another supercluster called Laniakea. And this picture, this purple kind of web-looking picture right here is exactly called that. It's called the cosmic web. And these are just countless numbers of galaxies that have this kind of intricate network, almost not too much unlooking like, the neural networks in your brain cells, is that the entire universe is structured as this kind of intricate web where galaxies and clusters of galaxies pull on each other, and they get to a larger structure called Laniakea in here, which is kind of a supercluster of superclusters. So I will post this video as a separate assignment because I'll post that. It's like only a couple minutes long, but you can watch that as a Google Forms worksheet of sorts, and get what you need to out of that, instead of playing it here for you. Moving right along, our closest galactic neighbor is the Andromeda Galaxy, also called M31. Here's a picture of it. It is in a group of galaxies called the local group. That is exactly that, is the closest group of galaxies to us. It is very similar to the Milky Way galaxy. It's a spiral galaxy. It is, a little bit bigger, actually a lot bigger. It's about 220,000 light years across as opposed to 100,000 light years. But this can actually be seen with the naked eye. If you go to a clear spot in the world where you don't have a lot of light pollution, you can actually see this structure. This guy is like a little satellite galaxy that's going around him as well. But, within here, you're talking, again, hundreds of billions of individual stars in that galaxy. This is the furthest away thing that can be seen with the naked eye, about 2.4 million light years away. And this is so, even though the entire universe is expanding, all galaxies are moving away from us, Andromeda is so close that it is colliding, in the process of colliding with the Milky Way galaxy, and our two galaxies will eventually become one giant galaxy that some scientists are referring to as the Milkomeda galaxy. Talked about that a little bit earlier in the slideshow, but the interesting part about that collision is that they're going to collide without anything actually colliding, is that even though it looks pretty filled with stuff, the majority of a galaxy is still empty space, and so the whole thing will collide without any two individual stars or any two individual objects colliding. It's just the structure itself will collide and become one giant new galaxy over time. But that's kind of an important exercise, understanding how much empty space. Even where there's a lot of stars, is still mostly empty space. So they will collide and move through each other and twist, not too much unlike what you see in this GIF that I was showing you before. Two galaxies, and they pull together with gravity and move through and spiral. Some stars get flung out. It tries to reorganize. So that'll be a cool thing, but that will be happening right around the time that our sun is dying. I think that's about 4 billion years away from now, so our sun should be, and it's getting close to being in its red giant phase around that time. Here's, again, the graphic I showed you guys before of what that will look like from Earth, is that the Andromeda Galaxy, while it's still this little smudge, gets bigger, then they start twisting together, and you wind up with, all this kind of craziness in our nighttime sky. So if we're still around to see that, that would be pretty cool. And here's just kind of a similar graphic. Andromeda's moving this way. Milky Way is smaller, so it's going to go further, but we got about 4 billion years. And Triangulum, and there's some other galaxies that are also close, dwarf galaxies, that will also get mixed up. But you have the Milky Way, Andromeda, Triangulum, you have the two Magellanic clouds will all kind of get twisted up. But this is kind of a graphic roughly showing their paths towards each other. In the nighttime sky, you can find the Andromeda Galaxy right off of the W of Cassiopeia. This is in the northern sky. Cassiopeia is a circumpolar constellation. It's kind of opposite the dippers in the north there. And if we did that star identification chapter first, we would have talked about that a little bit more. But Cassiopeia is this W-shaped looking thing toward the north. It never rises or sets, just does circles around the North Star. If you follow one of the points of that W to just below it, you can find Andromeda there. Again, you can't really see it around here because of the light pollution, but you're up in the mountains or out in the wilderness somewhere, you can see it. And here's an actual picture of it. You see the path of the Milky Way Galaxy in this long exposure photograph. You'll see the Andromeda Galaxy right here, and this is an actual picture of Andromeda with the Milky Way. So it's not too far off of the plane of the Milky Way as well. And just a distance comparison, Earth to the Sun is about 8 light minutes, Sun to the nearest star is about 4.3 light years, to the nearest galaxy is about 2.4 million light years, which is crazy to think. So when we are looking at the Andromeda Galaxy, we're seeing what it was doing 2.4 million years ago. And if they're looking at us, they would be seeing the same thing. They're seeing what would be going on Earth 2.4 million light years ago. And the last few things here. Other than Andromeda, you also have two small dwarf galaxies. They're regular dwarf galaxies. The small Magellanic Cloud and the large Magellanic Cloud, 160,000 and 200,000 light years away, respectively. But they are both kind of in orbit around the Milky Way. They're irregular dwarf galaxies. They can be seen in the southern hemisphere here on Earth, so we can't really have a good line of sight to them. But they are members of what we call the local group of galaxies and are orbiting around our own galaxy. Said as another term, the local group is the galaxy group that includes the Milky Way. It comprises more than 54 galaxies, most of them dwarf galaxies. The gravitational center is located somewhere between the Milky Way and Andromeda. If I make this a little bit bigger for a second here, you see Milky Way and all these other things. You have Andromeda over here. Let's move this out of the way for a second. So you have Triangulum, you have Andromeda, and all of these guys. So the Milky Way and Andromeda are the two big boys, and you have all these smaller dwarf galaxies kind of existing in that same space. So it's around 54 galaxies, referred to as the local group. Covers a diameter of about 10 million light years. And this group itself is part of the larger Virgo supercluster, which may be in part of the Laniakea supercluster, which they mentioned in that one video that I will have you guys watch elsewhere. So when we're talking about how we organize things, obviously you have Earth to the solar system. The solar system is part of the Milky Way. The Milky Way is part of the local group. The local group is part of the Virgo supercluster. And the Virgo supercluster is part of the Laniakea supercluster. which is in turn part of the entire thing that we refer to as the cosmic web. Okay, which the cosmic web is this crazy looking thing here. So again, watch this video. I will post it as a separate assignment, but some interesting things on a couple minutes. It's kind of like one of those like mind-blowing type of videos where you start just expanding out and out and out, and really thinking about what how big are the things that we're talking about here. Okay, so again, know this little sequence: Milky Way. Milky Way is part of the local group, the Virgo supercluster, Laniakea. Here's another view of the local group, and they have the different types of galaxies, but both Milky Way and Andromeda are in here, and some of the other smaller galaxies that are involved in that as well. And it's hard to put this stuff in one picture, but here's a picture of the Virgo supercluster. You have the local group in here, and then each of the dots on here are individual galaxies. So this is like, so if the Milky Way galaxy is our city, the local group is like a region of cities. So think like Pittsburgh and Detroit and Columbus and maybe Chicago. And that's the local group. And the Virgo supercluster is like our country, where, it has, from East Coast to West Coast, all these other things. And then you expand out past that, and using this analogy, you're talking obviously the world and things that are, the entire globe, that is, and things that are kind of bigger than we can even put in this analogy. So that's actually it for the slides. Kind of a short slide, so 32. I kind of moved a little bit fast through all that, but fit it in a normal class period, about 42 minutes. So you'll probably be able to break this whole explanation up over a couple days. But there's your notes. Explain everything you need to do. Again, just check Google Classroom for whatever the assignments might be. Okay, I'm trying to build up some of that stuff. Nothing too crazy. But everything you should need to know, unless it's assignment specific, could be found in this slideshow, either in this video version, or if you want to actually go to the slideshow and click through it yourself and read what it says in there, do that. But make sure any videos I post that you watch those. Like I said, this was a video in here. I might post that separately since I can't really play it very well within this video recording. So again, hope everybody is staying healthy and everything else is going well, and you guys aren't getting too stir crazy. But again, keep busy on school, and I know this all sucks, but in general, keep with it. Stay on top of your school, so that nobody gets behind. Everybody's grades stay good, and most importantly, obviously, stay healthy and follow all the precautions that the government and other important people are putting out there for you and everybody else. Okay. Have a good day. As always, email me with questions, and keep checking Classroom for assignments. Thank you.